Hi, welcome. This is the fifth session on elementary number theory. Today we are going to talk about congruences. Okay. And my point of doing congruences will be that much which is needed for group theory and abstract algebra. And if time permits, we will come back and do little more number theoretic results little later. Okay. Let us get started. So let us recall. We will assume n is a natural number and n is greater than or equal to 2 for the rest of the section, today's session. Okay, and we had already seen that if you give me any real integer a, okay, the division algorithm says that I can write this as m times n plus r, where m is an integer and r is, this is a very important crucial point, r is 0 less than or equal to r but strictly less than n. Okay, in particular, just to make sure that you follow. Okay, I done in the when I did division algorithm. Suppose I have something like my n equal to, let us say 6, my a is equal to minus 23. Okay, then what will be r? What is the division algorithm? Then, as I said, you think of this as an EMI. I have to keep paying EMI so that this debt can be completely paid off. That means what? That means I have to do minus 4 times 6. Okay, that will be 24, but I wanted only minus 23. Therefore, when I pay 24 rupees to the fellow who gave me loan, then he has to return 1 rupee to me. That is a reminder. You understand this? Okay, please. Otherwise, if you have not seen this, please go back. Okay, go back and review division algorithm. Okay, pause, review, proceed. Let me make sure that I'm sharing the screen. Yes. Okay. So now we want to make a definition. I want to define a relation. Okay. So I will define a relation. We want to define a relation. You may not understand the relation, but you might have heard the word equivalence relation. Okay. But we will get a relation and we will show it is an equivalence relation on Z using the division algorithm. Okay. For the natural number n. Right. How do I define? Give me two integers a and b in Z. I say a is related to b. I read this as a is related to b. Okay, if a and b leave the same remainder, when divided by n. Yeah. That is, when I write a as sometimes, that is a k times n plus r, where 0 less than or equal to r less than n, and b as some ln plus s 0 less than or equal to s less than or equal to, strictly less than n, then r and s are the remainder. Okay, r is the remainder left by a when divided by n, and similarly s is the remainder when b is divided by n. Okay, what do I want? We want r equal to s. Is that clear? So please understand. So for example, let's look at the earlier case. When n equal to 6, a equal to minus 23, the remainder is 1. And suppose I take something like 19, that is 3 times 6 plus 1. Therefore, minus 23 is related to 19. Okay, for example, when n equal to 6, minus 23 is related to 19, because minus 23 is minus 4 times 6, 24 plus 1. 19 is 3 times 6 plus 1. Therefore, the remainders are the same. Yeah? Okay. So this relation has the following property. In fact, it will be good, okay, take some other n as an exercise before you proceed further, okay. Just be comfortable, take some n equal to some now not equal to 6, something greater than 2, make strictly greater than 2 also, right, and find a and b, okay, something in the negative side, something in the positive side, and say that a is related to b. You understand the question? Please do that before you go further. Okay. So whenever you learn this kind of new concepts, okay, you first go through the example given by the teacher or by the book, and then immediately you stop it and you play with it. You create, you may or may not succeed, doesn't matter, but you play with it, you will see that you understand the concepts more and you also become very comfortable. Okay, this is the trick you have to learn. Okay, right. Now go back. So this relation has the following properties. What are they? Number one, if you give me integer a in z, then a is related to a. Why? Because when I, okay, it has the same remainder when divided by n. Okay, this relation, if you want to say, you have to say this relation depends on n. But since n we have fixed, I am not going to say, but to be very strict, to be very precise, what I call pedantic, you have to say a is n related to b. If a and b leave the same remainder divided by n. Okay, but since n we fix, we will not write it. Is that all right? Okay, the next thing is, if a and b are z, then a is related to b if and only if b is related to a. This is called reflexive. This is called symmetric. That is, the relation is called reflexive. This reflection is called symmetric. Right? That's the same thing. There is nothing. Right? What is the third one? Third one is, if a, b, c are given, and suppose you tell me a is related to b and b is related to c, then that implies a is related to c. Because a and b when divided by n leave the same remainder, b and c leave the same remainder, therefore the remainder of c also is remainder of b, but remainder of b is same as remainder of a, therefore a and c leave the same remainder. Is that clear? So review this PRP. So one usually says this n or this is an equivalence relation. Okay. So I do not go further into this, but again I will ask you to watch foundation videos. Only one video I think on equivalence relation. Okay, I will give in the description, I will give the link. So there is a remark for VKS, Vijay Kumar Sharma. Please give the link. Okay. So once I have the equivalence relation, then what are known as equivalence classes? Okay. Therefore, we have the notion of equivalence classes. But before going further, let me look at this in a different way. So when do I say A and B are related? If they have the same remainder when divided by n. This is the definition. But I claim this happens if and only if n divides a minus b, which is same as, or n divides same as n divides b minus a. Why? Because if a and b are related, what does it mean? My a is going to be some kn plus r and b is also ln plus r. the same remainder, where of course R is satisfy the standard condition, right? Therefore, what is A minus B? A minus B is K minus L into N, and B minus A is L minus K into N. Therefore, N divides A minus B divides. So, we have proved this relation, right? If A is related to B, then N divides A minus B. The next thing I want to prove is, okay, if N divides A minus B, we want to prove A is related to B or B is related to A, because it's symmetric, right? So no problem. Yeah, how will I do that? Let's look at. So by division algorithm, I can write A as again Kn plus R 0 less than or less than N. See, these are all unique. That we are using that fact of, and this I can write as Ln plus S 0 less than equal to S less than N, because I want to prove A is equivalent to B, A is related to B. That means I have to show when divided by A divided by N, A and B both leave the same remainder. But so let us assume the remainder of A is N, the remainder of B is S. What do you have to prove? You have to prove R equal to S, right? Suppose not. Okay, assume R is greater than S. Okay, and S greater than R also similar proof, right? Then what I can do is, let us look at A minus B. A minus B is K minus L N plus into R minus S, right? Now what is our assumption? Assumption is N divides A minus B. Therefore, if we look at R minus S, remember 0 is less than R minus, less than equal to R minus S. But since remember S is also non-negative, this will be less than equal to R, but this R is strictly less than N. Do you understand this? Is this clear? Right? I am going to make use of that. Now R minus S is what? A minus B minus K minus L times N. Right? Now this is divisible by N and this is divisible by N. Therefore, R minus S is divisible by N. Right? You remember divisibility, the first lecture in the ENT series we are using. N divides R minus S. Right? But remember R minus S is greater than or equal to 0. Suppose R minus S is strictly greater than 0. Right? If it is positive, if R is not equal to S, we are assuming that, right? Oh, we are assuming R is greater than S. Therefore, it is actually positive, right? Since R minus S is greater than 0, R minus S is a natural number, right? It's, and N divide that, therefore R minus S must be a multiple. Okay, call it M times N, where M is a natural number again, because R minus S is positive, N is positive, therefore M must be positive. But M is a natural number, therefore M is greater than or equal to 1. N is a natural number which is positive, therefore if I multiply Mn, that's greater than or equal to N, right? Therefore this is greater than or equal to N. R minus S is greater than or equal to N, right? But remember, we observed that R minus is strictly less than N. That's a contradiction. Okay, hence we conclude R minus S equal to 0, that is R equal to S. Yeah. If I have gone through division algorithm proof recently, in the uniqueness part is exactly the same argument I used. Okay. See, that is why one has to learn the proofs well. Don't learn anything for exam purpose. Okay, learn it, enjoy it, and review it. Next time when you see, you may not remember the proof, but you will see, something similar I have seen it earlier. Where was it? Then you slowly go through it. That means it becomes part of you. Okay, you don't have to make an effort to remember, but it actually becomes part of you. Okay, that is why revision is important. Okay, let's go by. So what have we shown? So this is a major result which you will use often. Okay, let me call it a theorem. It is a laughable, but it's okay. What is the theorem? A and B are in Z. N is a natural number. N greater than or equal to 2. Then A is related to B if and only if n divides A minus B. Is that okay? Right. So pause, review, proceed. Now we are ready to define equivalence classes. So this is, we saw this is an equivalence relation. Okay. So if you give me a natural integer z, then the equivalent class of A is the collection of all integers B, so that A is related to B, which is same as B in Z, so that B is related to A. Right? You understand that? Let's look at, okay, some examples. Let me take again n equal to 6. Okay. Let me look at 1. Okay. My A equal to 1. What is the equivalence class? What is the equivalent class of 1? Then what is the dimension? So if B belong to this, what does it mean? B minus 1 must be a multiple of 6. Therefore, it should be m times 6. You understand that? Therefore, what is B? B must be m times 6 plus 1. What is m? M is any integer. Right? Therefore, B, this one is exactly all 1 plus 6 times n or m times 6. All multiples where m varies over. Let me rewrite. 1 plus m times 6 where m varies over integers. Right? Let us write it in slightly longer notation. So I start with 1, then 1 plus 6 is 7, and 1 plus 2 times 6 is 13, and 1 plus 3 times 16 will be 19. You can see that 1 plus 6, 7 plus 6, 13 plus 6. Do you understand what this is? Without knowing, you can write it, right? And here it will be minus 1 will be minus 6, therefore it's 5. Sorry, minus 5, and this will be minus 11, right? 2 times. Minus 2 times 6 is minus 12 plus 1. And this will be minus another 6, it will be minus 17. Yeah, 3 times, minus 3 times 6 will be minus 18 plus 1. Do you understand? It goes on. Yeah. So, do you understand what this is? You must have seen what this means. You know this is, can you say? Yes, arithmetic progression. With the starting point 1 and common difference 6. Right? But usually arithmetic progression in high school is one direction, only positive direction. But this is arithmetic progression in both directions. So we will call it bidirectional arithmetic progression. Bi meaning 2. Do you like it? It's not simply equivalent class. Okay. Equivalent class of A is all B, so that A and B are related. Okay. You can just chant like mantra, but in a concrete case, you have an explicit example. Not only that, you relate it to something what you learn in high school. That's arithmetic progression. The only thing is this arithmetic progression goes both ways. That's it. Okay. Very good. Okay. Let's do say a little more about these things. Now, suppose, now let us take any A and again n arbitrary now. Okay, any A, and usually this equivalence class again to denote it depends upon n, we may denote by this. You understand that? But since we are fixing n, I will not write it. I will simply write this one. Okay, but if you want to be very precise, you have to write this is the equivalence class of A with respect to the fixed natural number n. Okay. Now suppose and B is in A, we already saw what does it mean. That means A minus B must be a multiple of n. Right? That means B must also be A plus I have written this way, but you can also write a plus mn. This is minus m1, don't worry about it. Yeah, yeah. Maybe write it b minus a, then b equal to a plus mn. Are you comfortable? Okay. Because b is equal to this means a and b are related, which is same as b and a are related. That means b minus a must be multiple of n. So b equal to a plus mn. You follow that? Okay. We will use it often. So how do elements in the equivalent class A look like? They look like a plus m times n, where m is any integer. Any element must be of this form. Is that all right? Okay. Right. Now we want to do something. Now I want to know, you fix n as usual. Okay. How many equivalence classes are there? Okay. How many equivalence classes are there? Suppose you give me a natural number a, sorry, integer a, then I can write it as some k times n plus r, 0 less than or equal to r, strictly less than n, right? Now notice that this shows r is in the equivalent class of a, or a is in the equivalent class of r. The same, right? A belongs to the equivalent class of b if and only if b belongs to the equivalent class of a. Why? This means a minus b is a multiple of n. Okay, but it's same as saying this happens if and only if yeah, n divides b minus a, but that means b is in the equivalent class of a. Okay, right. So come back. Therefore, a belongs to this r. Right. So given any a integer, okay, there exists this r unique. The remainder r is unique. How many such remainders are there? N remainders, n possible remainders, right? Therefore, for each a there is a unique remainder r which has to be between 0 less than or equal to r less than n remainder. Therefore, my a has to be in r, right? Now, therefore, the equivalence class of a and b are the same. These are the things which you must have seen in foundation, but quickly I will go through, right? Because anything here, what is the form? It will be of the form a plus m times n, right? You understand that? But a itself is k times n plus r plus m times n. Therefore, it is r plus k plus m times n, right? Therefore, if b is here, b is of this form, then what does this mean? B belongs to equivalence class of R. You understand that? Therefore, equivalent class of A is contained in equivalence of R. E or P. In a similar fashion, I can show if C belongs to the equivalent class of R, then C is of the form, let us say Kn plus R. Right? Now I want to say C belongs to the equivalence class of A. What is that I have to check? I have to check. Okay, but what does it mean, equivalence class of A? This simply means it leaves a remainder R, but C also leaves a remainder R. So in fact, that's the easier way. Yeah, let's go back. Suppose B belongs to this, if and only if B has the same remainder. When I say has the same remainder, when divided by n, etc., are understood. R, right? But that means B has to be in R. Because when does an element belong to this R? If both have, because R itself is 0 times n plus R. There is only one way of writing it, right? This is unique. Therefore, the r when divided by n, the remainder has to be r. Yeah, of course, condition on r is this. Okay. So what I have shown is the following. Therefore, given any a in z, okay, then there is a unique r such that 0 less than or equal to r less than n, such that equivalence class of a is same as equivalence class of r. Therefore, we had answered. Therefore, there exists n equivalence classes. So, pause, review, proceed. Okay, have you understood? You saw that? I just wanted to use two equivalent definition when a is related to b. Okay, I went to the standard number theoretic way of saying a minus b is divisible by n, but then I remembered my definition is they leave the same remainder, therefore the proof becomes much one line, much easier. Okay, that is the advantage of equivalent definitions. Okay, whichever is to your advantage, which makes your life easy, you can use it. Okay, right. So we know there exists n equivalence classes. Is that all right? Now I have to introduce some name. What is the title of this session? Congruences. Have I used the word congruent? No. Number theory always starts with that first, whereas I didn't do that. Okay, so it's time that I have to do. And number theory uses various words. We will see all these three. All the words are mean the same. We understand it properly. That's very important. Okay, let's go. So number theory. Let me use a different color now. If I give a and b in z, and as usual n is a natural number greater than or equal to 2, okay, we say a is congruent to b modulo n if n divides a minus b. Okay, this is written as a notation. Right. So this notation is same as what we meant by a is related to b. Right, a is congruent to b is same as a is related to b. Therefore, now this has three meanings now. One is a and b have the same remainder. And n divides a minus b. And third, a is congruent to b. All these are same. Therefore, our equivalence classes of a are also known as congruence classes. Okay, equivalence classes with respect to the relation this are also known as congruence classes. Okay. Now number theory also uses the same word. Now we saw any congruence class a, if given any a, look at the congruent classes, congruent class of a, that is the equivalence class of a, right? This equivalence class is same as the equivalent class of r, where r is the unique remainder. Right? Then usually some number theory books call this not some all residue class. Because residue means what is left out, right? What remains, that's why they call it remainder. Therefore any congruence class has to be a residue class for 0 less than or equal to or less than n. Is that clear? Yeah, pause the video, go back, understand. Okay, you should not get confused now, it's much easier. That's why I started with something, because in number theory many people don't realize, they prove it, but they don't realize divisional algorithm is some kind of a fulcrum under which everything revolves in the basic number theory till you go higher. Okay, go further. Okay, so learn that well. That's why I always pin my arguments using division algorithm. Okay, right. So we are done various things, and we are also seen equivalence classes, some examples, right? The next thing we want to do is we want to do arithmetic. That is, we want to do arithmetic. So let us denote Zn is by definition the set of equivalent classes, which is same as set of congruence classes. It is same as residue classes. Okay, equivalence classes modulo n if you want, modulo n and modulo n. You will keep hearing the word modulo. Okay, right. Okay, and therefore, what is the size of Zn? How many elements are there? There are n elements, right? Okay, good. See, now usually our number systems, are infinite. Take the natural numbers, integers, rationals, reals, complex numbers, they are all big. Now we have this Zn also I want to think of as a number system. When I want to think of a number system, what are the things I have to make sure? I have to say whether I can add, whether I can multiply. Okay, in algebra they are called binary operations. Can I add? One of the standard trick, again if you have gone through my real analysis course everywhere, I would tell you. So I know how to add two integers, two rational numbers, two real numbers. Now you are given me two equivalence classes, congruent classes, modulo n. Now I want to add, remember this is not a number, it is just a set, an infinite set of, okay, infinite arithmetic progression. Two such infinite arithmetic progression you have given me, I want to add. What does it mean? When I add, I should get yet another arithmetic progression of the same type. That is, each is a arithmetic progression with common difference n. So when I add them, I should get a third arithmetic progression with common difference n. Do you understand? That is, you add two equivalence classes, I should get an equivalence class of the same kind. Right? Don't worry, we will look at very concrete things. Okay, because I'm kind of targeting at second year BSc students. Okay, many times algebra you find difficult because this kind of thing one keeps on writing something, you take notes. It's better to think, understand why you want to do, then slowly you will see you will become comfortable. For example, the way you become comfortable with algebra, which was introduced in your 7th standard or 8th standard. Now you are comfortable, right? Manipulation of symbols, the same way you should become, right? Let's go back. So arithmetic is what I want to do. That is, you give me two equivalence classes A and B, then I want to add. If you want, you can again put an n, it depends on n. This is also n, this is also n. But we will not bother about such niceties. I want to define A plus B. A plus B. So it should be an equivalence class C. Okay, this is an equivalence class n, equivalence class. Okay, just put in this, I have to get. So I have to define this C. It should again be, this C should be an element of this n element set, what we call the residue classes modulo n, or the equivalence set of equivalence classes, or the set of congruence classes. How do I do? As I said, I know how to add two integers. If you give me a and b, I can add. So I can try to say a plus b is by definition a plus b. This means by definition you define the left side by the right side. Now suppose I have something like my n is 6, right, and this is equal to 2, a is 2, b is 3, then the equivalence class will be of 2 plus 3, that is equivalence class of 5, right? You understand? But then we had already seen this a, let us again take n equal to 6, suppose my a equal to minus 17 as I did earlier, b equal to 19. You understand this? Oh no, 19 is going to, yeah, 19 is good enough, yeah. Yeah. So make it 18. Oh, 18 also very bad. So let us see 7, 15. Okay, good. Okay, you'll see that. Now, what is A? If A is minus 19, okay, this is minus 17. I can write it as minus 17 as minus 3 times 6 plus 1. Therefore, minus 17 equivalence class is same as 1, right? And 15 is 2 times 6 plus 3. Therefore, equivalence class of 15 is same as 3, right? So, when you multiply minus 17 according to the first one, you will have minus 17 times 15, and here this equivalence class you would have done as 1 times 3, that is, this is much easier. Okay, this is 1 times 3 is 3. Oh, I have to add, sorry, I have to add, I forgot. Okay, 1 plus 3 is 4, right? Minus this one, how will I do that? Minus 17 times 15. So 10 times is minus 150, and 5 times 17 will be 85, minus 85 is, therefore it will be minus 235. I hope I am right. I may be making mistake. Please make sure that I am doing it correctly. Okay, 5 times 8, 25. Okay, right. 15 times 15. Yeah, that's easier. 15 times 15 minus 225. 2 times 15 is 30. So it should be 245. Is that right? 15, and 5 times this will be 30, 85. 35. Yeah, okay. Maybe I should do it 17 times 15 the traditional way. 5 times is 80, 35, 5, 3, 8, and 1, 7, 1, 7, 0, 5, 5, 255. Yeah. Oh, where did I miss the thing? Oh, 15 times 15, 2 times 15 must be 30 I have to add. Okay, yeah, right. Yeah. Okay, 15 times 50 is 225, plus 2 times 15 is 30, therefore 255, therefore it's minus 235. Now minus 235, I have to write it in terms of thing. Okay, how will I do that? See, I'm just doing all these things so that you will become easy, you will find it easier. Okay, this I have to divide by 6. So naturally 3 times this will be 18, and 55 9 times. Yeah. My, 235 is much easier, therefore minus 235 will be minus 40 times 6. That will be minus 240, therefore it will be plus 5. Oh, plus 4, right? Minus 240 plus 4. Am I making mistake? You see that? Doing arithmetic is difficult for me. Okay. This is alright, 235, 4 times this. Okay, 260, but whereas I want only 235, that means I have to add 5. Earlier, what did I do? Then did I do some mistake here? Minus 17 is minus 3 times 6, 18 plus 1, and 15 is 2 times 6 plus 3. Therefore, addition will be this. Yeah. Therefore, when I multiply minus 235, oh my gosh. Okay. I was stupid. See, I was supposed to add. You remember that? I was multiplying. That's why the main problem is. Therefore, minus 17 plus 15 will be equal to minus 2. Right? But what is minus 2? Minus 2 is going to be minus 1 times 6 plus 4. Right? Therefore, we get both the answers correct. I'm sorry for the goofing. See, I forgot. Even earlier you saw I was doing multiplication. Yeah? Because usually in the context of ring theory, one is doing. So anyway, is that all right? Okay, don't get confused. I was supposed to add. Therefore, I have to Minus 17 plus 15 is what I have to add, and look at the equivalence class of minus 2. Equivalence class of minus 2 is same as the equivalence class of 4. Okay? Do you understand this? Right. Now, what is that I want to do? So, you can see when I take equivalence class of A and equivalence class of B, then I could have done. But then you might have done A is same as equivalence class of A1 and B is same as equivalence class of B1. Then you would have defined it as A1 plus B1. So, what I'll have to say is these two equivalent classes are the same. Equivalence or congruence classes or residue classes are same. So, how do I do that? That is very easy. Now, if A equal to A1 and B equal to B1, then we have already seen the A1 is of the form some Kn plus A, right? A plus Kn. And similarly, B1 equal to B plus Ln. Do you remember? I did somewhere. How do the elements of same thing look like? Yeah. How do elements look like? If B is in A, then B must be of the form A plus multiple of N, right? Okay. So, we have done that. Therefore, what is A1 plus B1? A1 plus B1 is A plus Kn plus B plus Ln, that is A plus B plus K plus L times N, right? Therefore, A1 plus B1 is related to A plus B, and hence the equivalence classes of A1 plus B1 is same as the equivalence class of A2 plus B2. So, pause, review, proceed. So, you take two equivalent classes or two congruent classes. I want to add to get a congruent class of the same type. Okay, how do I do that? The easy trick is to take any element in the equivalence class, first equivalent class, take any element in the second equivalent class, add them, they are integers, add them, you get an equivalence, you get an integer. Now look at the equivalent class of that integer, right? What is the problem here? You may choose some A1 in the equivalence class and B1 in the second, and yet another person may look at A2 and B2 in the equivalent classes. So what you want to say is equivalence class of A1 plus A2, A1 plus B1 is same as the equivalence class of A2 plus B2 or anything. Okay, we proved with certain particular integer, we are equal to 6, A equal to minus 17, B equal to, I don't remember, 12 or whatever, say 15. Okay, and then we proved general case. Okay, right? Please go through the proof. This is what is called well defined. That is, it is independent of your choice of the integer in the equivalence class, right? I am supposed to add two equivalence classes, but what I am actually doing is I am adding two elements from each of the classes and then form the equivalence class of that sum. Okay, so there may be many choices. So we have to say it's something like, okay, if there are among, let us say in a nation there are five parties, right? Then I want to know, there is some question we want to ask, then I want to ask each party's opinion. Then I may ask only one representative from each of the classes. But if I choose a different representative from the same party and if he gives a different opinion, then it's not uniform, right? So it must be the same. Don't get confused. Just to try to give an analogy why it is important. Okay, right? You understood this? Very good. So we have done this. Then what remains? Next is we have defined. We said arithmetic. There is one more thing which I have to do. What is that? Multiplication. I am sure now you can come up with your own. What is that I want to do? Suppose I take equivalence class of A and equivalence class of B. I want to define equivalence class of A dot or times equivalence class of B must be equivalence class of C. How do you think you will define? I am sure you know that, right? Yes, we are going to define what you guessed it correct. So the way we want to define is this. So A times B we define to be the equivalence class of, see, A and B are integers, right? So then the same, right? So look at the equivalence class of. So the same problem. Suppose this is equal to A1. What does it mean? Take one representative A1 here, but then we know the equivalence class of A1 is same as the equivalence class of A. And equivalence, similarly take a B1 here, then equivalence class B1, right? Then I could have defined this to be A1 B1. The question is, are they same? Whether the equivalence class are the same, right? How do I do that? It's exactly the same way. Since A1 belongs to this, I know A1 must be some A plus Kn, right? And similarly B1 must be B plus Ln. Is that okay? Then what is A1 B1? A1 B1 is A plus Kn times B plus Ln, that is equal to AB plus A times Ln, so therefore Al, the n is common, and then Kn times B, n is common, therefore plus Kb plus Kn times Ln, that is Kln is common, n is common. You understood that? Therefore A1 B1 minus AB is Al plus Bk plus Kln times n. Therefore A1 B1 is related to AB. That means equivalence class of A1 B1 is same as the equivalence class of AB. Is it easy? Yeah. So again the same kind of well-definedness, right? Notice that you have an infinite set A, an infinite set B. We want to get another infinite set, and each is the arithmetic progression, and arithmetic progression with common difference the same n. Okay, but how did you do that? It looks like a very abstract thing, but life is actually easy. What we have to do? Take two elements in the equivalence class and multiply them out. I get an integer. Look at its equivalence class. That's it. Now what we want to do by saying well defined, if somebody else chooses different choices, he gets a different integer C1, that equivalence class of C1 is same as the equivalence class of C or AB. That's what we prove. Okay, you understood that? Very good. Okay, now it will be a good idea. This is very nice. Theory is over, but the best way to get hands on that will be to look at some particular example, work out the details. Okay, let us do that. So let n equal to 6. Therefore the equivalence class, okay, Z6, I'll write it as 0 1, that is I am writing only in terms of residue classes. There are 6 elements, right? I'll simply write it as 0 1 2 3, right? Therefore I want to say 0 1 2 3 4 5, and above you write it as 0 1 2 3 4 5. Now what I have to do is this. It's like a multiplication table. I have to write addition table. That is, if I add 0 plus 0, what will I get? 0. 0 plus 1, I'll get 1. 0 plus 2, I'll get 2. You have to check that, okay? Don't take it for granted, this one. But when I take 1, 1 plus 0 is 0 plus 1, and the equivalent class of that will be 1. 1 plus 1, the equivalent class of that will be 2. 1 plus 2, the equivalence class of 3 will be 3. 1 plus 4, the equivalence class of 4 will be equivalence class will be 4. 1 plus 4, equivalence class will be 5. But when it comes to 1 plus 6, 1 plus 5, it is 6. But 6 is, what is the remainder? 0. Therefore, 1 plus 5 is 0. Do you understand? Just for fun, let me do something else differently. Suppose 3 plus 0. 3 plus 0 is 3. And 3 plus 1 is 4. 3 plus 2 is 5. But 3 plus 3 is 6, the remainder is 0. And 3 plus 4 is 7, the remainder is 1. 3 plus 5 is 8, divided, the remainder is 2. This is the way. Do you understand this? Okay, I am not writing this because we are running out of time. So, okay, complete this. You understood what I am doing? So, there are two things we are looking at. What are they? This is a multiplication table, is like addition table is what I am writing, like multiplication table. You followed that? Okay. The next one we want to do is multiplication table. Let me write the same way now. Okay. 0, 1, 2, 3, 4 and 5, and above 0, 1, 2, 3, 4, 5. Okay. Okay, now what I want to do, this is a multiplication what I want, right? So let us look at 0 times 0, 0, okay, 0, 0 times 1, maybe I will use a different thing, 0, 1, sorry, 0 times 1 is 0, 0 times 2, these are 0, no problem. Now 1 times 0, again no problem, is easy. Now let's come to 2. 2 times 0 is 2, 0, equivalence class of 0. 2 times 1 is equivalence class of 2. 2 times 4 is 2 times 2 is 4, equivalence class of 4. 2 times 3 is 6, equivalence class of 6 is 0. 2 times 4 is 8, equivalence class of 8 is 2. 2 times 5 is 10, equivalent class of 10 is 4. Right? Now similarly 3. 3 times 0 is 0, 3 times 1 is 1, 3 times 2 is 6, that is 0. 3 times 4 is 3 times 3 is 0, right? 3 times 3 is 9, sorry. I'm sorry. I have just added 3 times 2, 3 times 3 is 9, that's correct. Therefore, the equivalence class is 3, right? 9, remainder is 3. 3 times 4, 12, equivalence class of 12 is 0. 3 times 5 is 15 to 12, therefore equivalence class is 3. Make sure that I am writing it correctly. Okay, I tend to make mistakes. Okay, now let's look at 4. 4 times 1 is 4. 4 times 2 is 8, therefore equivalent class is 2. And 4 times 3 is 12, equivalent class is 0. 4 times 5 is 20, equivalent class is 2. Right, 18 plus 2. 4 times 5 is, oh, this is 4 times 4. 4 times 4 is 16. 16 will be 12 times 4, 12 plus 4. Okay, 4 times 5 is 20. 20 will be 18 plus 2, therefore 2. Okay, now come to 5. 5 times 0 is 0. 5 times 1 is 5. 5 times is 20. Sorry, 5 times 2 is 10. 10 is 6 plus 4, therefore equivalence class is 4. And 5 times 3 is 15. That we already saw. 12 plus 3, therefore 3. And next is 5 times 4 is 20. 20 is 18 plus 2, therefore 2. And 5 times 5 is 25. 25 is 24 plus 1, therefore 1. You understood this? Okay, please do that. Okay, don't take me for granted. There is a possibility I might have made a mistake. But what I want you to observe is some of the very interesting things. Look at that. 2 is not the 0 element. And similarly, 3 is not the 0 element. Right? But 2 times 3 is 0. Okay, 2 is not the 0 element, right? 3 is not the 0 element. Right? If you want, equivalence class of 2 is not the 0. Right? Similarly, 3 times 2. Yeah, 3 times 2 is 3 times 2 is 0. And 3 times 4 is also 0. Right? Now, similarly, you can see 4 times 3 is 12. 0. But when it comes to 5, you see something interesting. Okay, nothing. In fact, we see 5 times 5 is 1. That means it's something like reciprocal of 5, whatever it may mean. 5 is itself. Okay. So I'm sorry. As usual, I forgot to share. Okay. Let's go back. Yeah, it's a problem in my thing. So this is the multiplication I want to do. Okay. You must have heard something which I said. Let's quickly go through. 2 is not 0 element. 3 is not 0. But 2 times 3 is 6. The remainder is 0. Right? Whereas 2 times 4 is 8. Remainder is 2. And 2 times 5 is 10. The remainder is 4 when divided by 6. Okay. Similarly, we can do that. 5 times 2 is 10. The remainder is 4. 5 times 3 is 15. 12 plus 3, 3. And 5 times 4 is 20. 18 plus 2, 2. 5 times 5 is 25, which is 24 plus 1. This is it. Okay. So you can complete this table as I did. What I want you to observe is you write it and see there may be two equivalence classes which are not 0 equivalent class, but their product is equivalent class. Okay. And the only thing is when it comes to 5, you can see 5 times 5 is 1, the equivalent class of 1, because 1 is something like identity, right? We are multiplying everything, we get the same numbers, right? Like typical 1 in integers, real numbers, rational numbers. Okay. Then I would expect 5 times this 5, its reciprocal will be 5 itself. Okay. Right. So I think that's enough. Please go through it. And the best way to become very confident is choose some other natural number, small number. Okay, 5 or 7, something. Don't choose 3 or something. Okay, you also choose 3, but then you should go to something bigger, 7. Okay, or 8. Do it. It's a little boring, but do it. But you will become comfortable. You will become comfortable with congruent classes. You will become comfortable with arithmetic with congruent classes, equivalence classes. Okay, this is very important. Not only number theory. Okay, this is actually used in all your digital transaction in an indirect way, in a different way. Okay, it's a very important concept. Learn it, and more importantly, it will be very useful for your algebra. Okay. I hope you enjoyed the lecture. We will meet again. There are few more things which I have to work here to make algebra, okay, to be useful in algebra. We will do it later in the next lecture perhaps. But this is good enough for me to continue with my group theory. So I may, then my next may be in group theory. Okay. So stay tuned. Take care. We'll meet again.